Okay, so we've seen how Fischer, in his experiments using the Kiliani-Fischer synthesis and the rough degradation mechanisms, slowly developed an understanding of what the structure of glucose is, both its linear structure, which is the same for any kind of aldohexose, and its specific stereochemical structure that has to do with its orientation in three-dimensional space. But there were certain flaws in the model that Fischer put forth, which were borne out by certain outlying reactions which did not conform to the predictions you might make using the Fischer model we just discussed earlier. So in this part of the video, we're going to look into what those outlying reactions are, and then we're going to look into what kind of alternative structures glucose can exist in, and then some specific reactions that it participates in. So the first observation we have here is that there are no reactions with 2,4-DNP and NaHSO3 seen. So you know that the sodium bisulfite addition and the 2,4-DNP addition are characteristic of all kinds of aldehydes. So we should be able to see these reactions, yellow and white precipitate that confirm that these are aldehydes, but those reactions are not shown. So you might think that because of the preponderance of OH groups, alcohol groups in the glucose chain via some inductive effect or some other kind of effect, the reactivity is somewhat modified. But that's probably not the case, because we have two other outlying reactions here. The first is the reaction with MEOH. Now this is actually a reaction with MEOH and HCl. You can basically think of it as if you have some kind of alcohol group over here, and it's equivalent to if a methyl carbocation were to come and replace this. So you would have something like this, where you have a methyl carbocation coming and interacting with an alcohol and giving you methyl ether. So in this particular reaction, we have two different products forming when it reacts with this alcohol. So there must therefore be two different structures in which glucose exists prior to that reaction, or at least two different structures it exists in when it goes through transition states of that reaction. And finally, when we look at the reaction with acetic anhydride, again we get two different pentaacetate. So this reinforces the supposition we have that there are two different structures glucose exists in. But on the other hand, it also gives us some more information in that these do not give any oxidative tests, which means that the aldehyde group is somehow lost in these two structures. So we got to now try and see what kind of other conceivable structure we can come up with. Okay, so this is the Fischer projection of glucose, as we've seen before, with one aldehyde group, and then OH is in this particular configuration D, L, D, D, and then one primary alcohol group. So this is the model corresponding to that. You can see that there is the aldehyde group represented by this blue orb here, this blue ball. The H's are represented by the green and in this case the yellow orb. The yellow ball represents the H which is on the switched position on the chain. The red balls represent the OH groups, and this black ball at the end represents the primary alcohol, which is achiral, and therefore its substituents haven't been shown in the model. So we need to now show for ourselves that this model actually matches that Fischer projection in its stereochemistry. Recall now how the Fischer projection is defined. The Fischer projection is defined by saying that you have this group on the right and this group on the left when the vertical carbon-carbon bonds on the Fischer chain backbone are going away from you. So let's focus on the penultimate carbon of this chain. As you can see in this model right here, the penultimate carbon has two carbon-carbon bonds going along the chain, one upwards and one downwards, both receding from the viewer. In this particular configuration, the OH group is on the right and the H group is on the left. So we can clearly see that this matches exactly what we see in the Fischer projection model. However, this is shown as a typical zigzag structure of organic compounds. When we come to the second carbon, therefore, the carbon-carbon bonds are shown going inward into the plane. The carbon itself is receding. So to correct this, to make it in line with what we've seen in the Fischer projection, we need to rotate this. When rotated, and when the entire model is correctly rotated and oriented, what we can clearly see is that if the vertical bonds recede into the plane of the figure, then the OH is on the right and the H is on the left, just as shown in our model. Again, we need to perform a similar rotation for the fourth last carbon. form this rotation. And in this particular case, we can clearly see that the H is on the right and the OH is on the left. Okay, so I hope these are all equally clear to you, these three groups. Coming to the fourth group, again we can see that it's going backwards into the plane, so we need to reorient it. Now, as you can see, the carbon-carbon bonds are going back into the plane, and now we have the OH on the right and the H on the left. Again, that matches the topmost carbon. The first carbon, the alkyl or aldehydic carbon over here, has a certain defect in this model. The defect is that these models are made for sp3 hybridized carbons, okay? Whereas this should actually be an sp2 hybridized carbon, and it should therefore be entirely within the plane of the molecule. Now, if you look at what we've done, you should realize something. What you should realize is that the Fischer projection is not defined for when you look at the chain as a whole. It's defined for when every single carbon has these vertical bonds on the Fischer projection going backwards into the plane. And therefore, the Fischer projection actually tells us what the stereochemical configuration of this molecule is when it is viewed in a somewhat ring-like shape. Okay? So now we can see that we can examine reactions in the light of this ring shape. And that's what we're going to proceed with to understand the alternative structure of glucose. So we've seen that it's folded up into that one possible conformation, one possible folded conformation of this Fischer projection here, which is just what you get when you actually apply the rules for the Fischer projection over each successive carbon, is this kind of cyclic structure where we saw that for each carbon, we're actually fitting the specified stereochemistry. Now this cyclic structure can be seen from this side with everything on the left facing the viewer, or it can be seen from this side with everything on the right facing the viewer. The convention is to take the one with everything on the left facing the viewer, so you can check for yourself that these actually come in the order shown over here. The aldehydic carbon, if you look at it with everything on the left facing the viewer, ends up at the bottom. So this is the second carbon, this is the third carbon, the fourth carbon, and the fifth carbon. And you can check that the stereochemistry specified over here exactly match on this model. This is a diagram that we've created that represents what the structure is going to look like if we look at it from this side, with the molecule shown on the wedges coming out of the plane towards the viewer, and the molecule shown on the dashed wedges going into the plane and therefore away from the viewer. I'd encourage you to pause the video for a minute and check for yourself that there is a correspondence between these structures. Remember that this particular carbon, which has been shown as an sp3 carbon because of the limits of models, chemical models, is actually an sp2 carbon, and this aldehyde is therefore in the same plane as this carbon and this carbon. Okay, now the next thing we've got to see is what is the alternative structure of glucose that can explain the reactions that we just covered. Okay, now this alternative structure obviously can't just be this. This is just a different conformation of the atoms. Atoms rotate around bonds, that is to say sigma bonds, not pi bonds, all the time. They assume different conformations except those which are prohibited by steric energy costs, and therefore this is not going to react chemically in any different way from the straight chain, from the absolutely straight out zigzag structure that we started with in this model. Why then am I bringing up the structure at all? Because this structure gives us a very elegant way to visualize how a particular reaction takes place, whereby this is going to get converted into a truly cyclic molecule, and a bond will form over here that closes the cycle. Now we'll have to take it on faith for now, but I will show you later why this has to be the case. But the reaction to cause the cyclicization is going to be between the aldehydic group over here and this OH group receding into the plane from your perspective over here, which is the C5OH. Now, for the C5OH to react with the aldehydic group, they must be close to each other. And since the C5OH is receding into the plane, that is not right now possible. This OH needs to be brought into this plane. Okay, you can see from this diagram, you can see from the model that OH is receding, from the diagram that OH is receding, and if you look back at the Fischer projection, everything on the vertical backbone, including the aldehydic group, because this carbon is planar, has folded up into the ring. So anything on the vertical substituents has to obviously be either entering or exiting the plane. Since this OH, this penultimate carbon's OH, is in the horizontal part of the Fischer diagram, it's not going to be in the plane. So what we're going to do here is we're going to perform a rotation around this single carbon-carbon bond, and we're going to get this OH into the plane. That is, it's going to replace where this CH2OH is right now. If we perform this kind of rotation, let's see what happens. Now the OH is in the plane and it's near this aldehydic O. In this particular case, what's happened now is the CH2OH is coming out here and the H is going in. So we've effectively obtained a structure where we have this as an OH, this as a CH2OH, and this as an H. This could also be seen by simply performing an even number of switches on this Fischer projection. You could have this OH and this CH2OH have a switch. But once you've done this, you've upset the stereo configuration, so there's going to have to be a switch between this new CH2OH and this H over here as well. And that means that the CH2OH will ultimately end up where the H was, and the H will end up where the OH was. The OH will end up where the CH2OH is, just as shown in this diagram. Now that we've seen that a reaction does take place in this particular configuration, let's look at what the reaction is. The reaction is a familiar formation of a hemiacetal, and the reaction pathway is mentioned here in case you need a quick refresher. What happens is that an alcohol with some group R dash reacts with an aldehyde with some group R and forms R dash, O, and then this carbon with the R and its hydrogen attached, and the aldehyde oxygen opens up and forms an OH due to the transfer of a proton from this group to this group, opening it up as an alcohol and keeping this as an ether. This alcohol-ether combination on the same carbon is what we refer to as a hemiacetal if it formed from an aldehyde. And if there were two ethers, it would be an acetal. If this formed from a ketone, it would be a hemiketal and a ketal respectively. But generally speaking, the terms acetal and hemiacetal are used generically. All of this you should be familiar with, but this is just a brief recap. So let's see how this takes place in the realm of sugar, of monosaccharides like glucose, like D glucose. I recall that D glucose is this particular enantiomer of the monosaccharide glucose. So let's look at the two different ways it can cyclicize. The final OH, which we brought into the plane, has caused this CH2OH to come out of the plane towards us and has caused this H to go into the plane. This particular way of denoting something is known as a Haworth projection. Recall that when we form the cyclic structure of glucose, we always put whatever's on the left side of the Fischer projection above the plane and what's on the right side below the plane. In a Haworth projection, instead of using wedges and dashes, this is just shown by having straight lines that go above or below. And in this particular case, this OH which we had here has reacted and formed the hemiacetal. Okay, but there are two different pathways whereby this OH can react and form a hemiacetal, because this aldehydic carbon will now bear an alcohol and a hydrogen. And now, since it's formed a closed ring, the alcohol has to be either above the plane or below the plane. When the alcohol is below the plane, it is known as alpha D glucose. When the alcohol is above the plane, it is known as beta D glucose. Okay, so let's see what's happening exactly and why. So let's see what's happened over here. Okay, generally we depict it like this, and now since you've understood how the model works, you will see why this depiction is quite wrong, but it's the conventional depiction, so we still have to go through with it. Okay, what happens is, let's say this is basically the carbon that used to have a double bond and an H. Now it has an OH and an H, so that I've drawn over here, and it has this O connection to R dash. Now which of these alcohols did it react with? It reacted with the C5 alcohol in the model. So we draw it like this. But actually this is a wrong drawing. This is a wrong drawing because if this is the case, then this bond is going back into the plane and this bond is coming out of the plane. And that's not quite how it is. This entire ring this O-ring, you can imagine it as if it was a frame that I could lift and pull above this or swing below this. So this entire O oxygen ring has to be behind the vertical backbone. It's piche. You have to envision it like that. Why is that the case? Because as we know, what has actually happened is we've done a double switch over here, and this H has come here, CH to OH has gone there. This is the CH to OH, it's come here, and the OH, this OH is actually here, and therefore this bond is like this. This bond is like this. Now you can see how it's a ring and it can go behind it. But unfortunately, we generally don't do this. We always draw it based on the original Fischer projection. So we still put this guy at the bottom here, make the bond like this and put the hydrogen here. This leads to a certain amount of confusion. Remember the rules. The rules are very clear. When we put this, when we translate this into a Haworth projection like this, everything on the left hand side goes above. So H, OH, H. But this one, though, when we draw the Fischer projection of the cyclic structure, we draw it like this. It is drawn to actually resemble the Fischer projection of the straight structure. And therefore, it's wrong, basically. You must remember here there's been a switch, and so the CH to OH will come on top and H will go to the bottom. Though the H is on the left hand side here, it will go to the bottom. That is why for a cyclic structure, we always prefer drawing the Haworth structure, because the rules for the Fischer projection are derived from the Fischer projection of the straight structure. Fischer projections are not meant for cyclic structures. For cyclic structures, please use the Haworth projection always. Let me draw attention to another interesting detail. Because it was D, the CH2OH came on top. Had it been L, then the entire oxygen ring would have formed on this side. And in this case, H would have been on the right, so it's supposed to go down, but there's an inversion. So H would have been up and CH2OH would be down. So this, by looking at whether CH2OH is up or down, you can tell if it is D or L. You don't need to open it up and do double switch and figure all that out. Just remember that it has to be up for it to be D, because the H should have been up, but now the H has become down, which is a really weird way of remembering it. But that's the basic logic. If the CH2OH is up, or rather if the H is down here, it's D. If the H is up here, it's L. So looking at this conformation will tell you D or L. But there's another thing that's happened here. Look over here, this carbon, which was previously achiral, has achieved chirality. It's got an OH, an H, an R, and an OR. An ether, an alkyl group, a hydrogen, and a hydroxy group, or an alcohol group. These are 4 distinct groups. Now it is chiral. Now the OH will either be below or above. Now what do we do? Again, this is defined in a really, really bad way, okay? So what it says is, on this Fischer projection, if the OH is on the same side as this last OH would have been, okay, as the so the C5OH actually, we know it's come down, right? We know the C5OH is, oh my bad, I'm still using the L structure. 1 second, I'll just revert to the D structure. So if this is my D structure, sorry for using the L structure and not switching back, this is my D structure, then the OH would have been on the right hand side. Actually now the OH has come to the bottom and the switch has happened, but before anything the OH would have been on the right hand side, which means had it survived without any of this switching happening, then the OH would have been below and the H would have been above. If the new OH and H pair that has been created by hemiacetalization, if that has the same direction, that is the OH is below, here also the OH would have been below before this entire cyclization process took place, the OH would have been below, right? So then this is called alpha D glucopyranose, okay? And if instead this were to go above, then it would be called beta. So is it opposite to or is it same as the configuration of the last chiral carbon? Okay. Now you must understand this. The definition says last chiral carbon. It does not say the chiral carbon which became bonded over here. In other words, if for instance this was a 7-membered ring, 7-membered chain, sorry. Okay, then what would happen over here? Instead of this being just CH2OH, it would be CHOH, this group, attached to CH2OH. You can take a moment to pause and check that what I'm saying makes sense. All I'm saying is that if this was 7 members long, it would still have formed a 6-membered ring, because 6-membered ring is the most stable. So when it closes up, there would be CHOH and CH2OH sticking out, right? So still, it would not be defined anymore. The D would not be defined based on this carbon. This time the D would be defined based on, not based on this carbon, no, but based on this carbon here. So again, it's always based on, if you go back to the Fischer projection, what does it match with? This is why I'm teaching you this wrong Fischer projection. This Fischer projection is chemically wrong because actually they have switched positions. But without showing the switch, if we make the Fischer projection, then and only then can we tell what is alpha, what is beta. Okay, it's alpha if it's at the same side as the last chiral carbon. So in this 7 long chain, it's this chiral carbon we're talking about. When it was 6 carbons long, we're talking about the carbon which had itself become involved in the hemiacetalization process. But if it's the same direction as that last chiral carbon, then it is alpha. Otherwise, in the flipped case like this one, it is beta. And that brings us to a conclusion of what the structure of glucose in solution looks like. We know it has 2 major forms now. It forms a hexagonal structure, and it can either form alpha or it can form beta. And these are the 2 major forms of glucose in solution. So answering the previous question, where you were supposed to find the structures of alpha L and beta L glucopyranose, what you can see is whatever structures you got for alpha D and beta D, you simply need to invert the stereochemistry at each and every carbon. So you would get a structure like this. Right, you would get a structure like this, and then you would get something like this, right, when you change each and every position. So this is the answer to the previous question, and this is for obviously alpha L. You'll get a similar structure for beta L if you invert the position at each and every one of the carbons along the beta D form of glucose. You might be confused about the last the anomeric carbon, the C1. And the trick over there for C1 is that yes, the above and below has changed there, but that's because the reference stereocenter, the C5 stereocenter, where we were saying it is alpha if the configuration matches C5 and it is beta if the configuration is opposite to that of C5, will now also be ulta, because the C5 stereocenter will have a switched configuration, and therefore the C1 stereocenter, which is created by the cyclicization process, will also have a switched funda. So now alpha will mean above and beta will mean below, just because the same has happened for the last carbon, the C5 carbon, which has switched from being D to being L. So now the next topic is the pyranose and furanose structures of cyclic sugars. Okay, so there are 2 common resonance structures that you may have studied already in organic chemistry: furan and pyran. Furan, you can see it's like aromatic because you have clearly 6 pi electrons that have a complete resonance. In pyran also you have 6 pi electrons, but unfortunately they don't have a complete resonance, so this is a little less stable than furan. Both of these are very similar to the structures that you get when you have your cyclic sugars. In fact, I think you're already able to see that when you look at pyran, if you remove these double bonds and you add the H's and the OH's, this is basically the structure you have, right? It's a 6 vertex polygon with basically a hexagon with one vertex being an O atom. And for this is a pentagon with one vertex being an O atom. So you can just remember this as saying a furanose is a pentagonal sugar and a pyranose is a hexagonal sugar. It's as simple as that. So to see how these pyranose and furanose structures are interpreted in terms of sugars, let's first start with alpha D glucopyranose. In alpha D glucopyranose, as we've already covered, you can see this is D because the H is on the left hand side, and you can see it is alpha because the OH is exactly where the OH of C5 would have been. Now these have cyclicized, they form a structure like this. It has 1, 2, 3, 4, 5 and 6 vertices in the structure. So it will form a hexagonal structure just like what we saw before. However, there is also a possibility wherein this will interact with the C4 OH. When it interacts with the C4 OH and forms a similar structure, we have 1, 2, 3, 4 and 5 vertices in the sugar ka cycle, which is why this is a Fischer projection, as we've already said, and when we convert this as corresponding Haworth projection, this is the Furanose structure, which is known as alpha D Glucopyranose, in contrast with alpha D Glucopyranose. In the Haworth structure, we follow the same logic as before. This is alpha, so H is above, OH is below. These are just shown as they were. For this one, where the OH had to be rotated into the plane, what has happened is the H has gone to the bottom instead of being on the top as it would normally have been, as it was in this previous case also. So the H will go to the bottom, and this entire group, CHOH, CH2OH, will move to the top of the Haworth projection. And this is alpha D Glucopyranose. One clarification should be made over here. That clarification is that when we talk about alpha, even for a furanose sugar, it is always defined with respect to the penultimate carbon, not final carbon. Final carbon is obviously achiral, to the penultimate carbon or the final chiral carbon. So it is defined with respect to C5. If this had not been this kind of structure, so let's just assume that the H was here and this had been the OH, then the cycle would have formed on this side, right? But this would still have been alpha. It is not defined, alpha and beta are not defined with respect to the carbon participating in the cyclicization process. They are always defined with respect to the final stereocenter of the Fischer projection. And the final stereocenter is still this carbon, even though it lies outside the ring. So you must always remember, when you're asked to nomenclate alpha and beta sugars, always look at the final stereocenter and decide accordingly whether it matches or whether it is in opposition. Right. So the thing that I want you to all to realize now is the number, the sheer number of isomers that we have familiarized ourselves with. What is the number of isomers? What is the number of isomers that fit in, that come in over here? Okay, so just for D glucose, let's see all the different isomers we have. We have the straight chain isomer, we have alpha and beta pyranose. And we also have this corresponding furanose. I'm sorry, it's come out to be a little bit slanted because of the way I've written it. So we have the straight chain isomer, that's 1. We have alpha pyranose, beta pyranose, alpha furanose and beta furanose. So we have a total of 5 structures. Okay, the most common structures, quite obviously, are going to be the alpha and the beta glucopyranose. This is because this is an internal reaction that's taking place, so the hemiacetal will form relatively quickly. Okay, once this hemiacetal has formed, okay, as in this particular case, which is more, if it forms a furanose structure, there's going to be more steric strain, because as you know, a 5-membered ring has more steric strain than a 6-membered ring. Though a 5-membered ring is the ideal condition for a planar compound, a 6-membered ring is able to adopt the chair configuration, as we have studied when we studied the conformational analysis of cyclohexane. And in this chair conformation, which is something like, if this is the chair, then it will be something like this, where this represents one carbon, this represents another carbon going off here, and this is the flat part of the chair. So when it assumes this chair conformation, the six-membered ring is more stable, and hence the alpha and the beta glucopyranoses will be more stable than the glucofuranose forms. Okay, so that gives us 5 different isomers for just D glucose. Okay, if you remember the formula we derived at the beginning of the chapter, we have 2 to the power n minus 2 different isomers of just aldohexose, stereoisomers purely. So this D glucose is one of 16 different forms of aldohexose, each form having these 5 other isomers of themselves. So you have a total, if you're asked the total number of isomers of aldohexose, it's going to be, including cyclic isomers, it's going to be 16 to 5, that's 80 different possible isomers. Just think about that. If you're asked what the number of stereoisomers is, it's a slightly trickier question. Remember that the alpha and the beta actually come into the play of geometrical isomerism. They're not strictly speaking optical isomers. So you might want to include the alpha and beta separately and say that there are a total of 5 basic configurations or 5 basic isomers. When you include stereoisomers, depending upon how the OHs and Hs are arranged, you can have glucose, mannose, galactose, talose, indose and the rest, all of them with D and L configurations. So total of 80 different isomers of aldohexose. If you follow the typical pattern of learning chemistry, this is probably the highest number of isomers of a single compound that we actually formally categorized so far. So take a moment to understand this properly. We now come to another topic called mutarotation. Okay, the word mutarotation, you can clearly see, is itself made out of 2 different elements. There is muta for mutation and rotation. Okay, so we know that each of these optically active compounds, which are basically the compounds that have multiple chiral stereocenters, have this property in them that they can change the plane of polarized light. So if you have plane polarized light coming in such that the vibration of the EM waves is happening in a particular plane or in a particular direction, then that will be rotated. It's basically a form of circular polarization, which these molecules are capable of performing. So the question is, when you have a particular isomer of glucose, it has a particular specific rotation. A different isomer of glucose will have a different specific rotation. When you put any isomer of glucose in solution, the isomers begin to convert from one into another. This process is known as mutarotation. That is the mutation of the rotation, so to speak. Okay. So there are 2 main facts that we need to keep in mind before we delve into the topic of mutarotation in more detail. Okay. One is that all isomers of D glucose, okay, these all isomers of D glucose are interconvertible. All isomers of D glucose are interconvertible. I have taken this as a specific example. This is true for any of the 16 stereoisomers of aldohexose, or for that matter for any monosaccharide. So just as I say, all the isomers of D glucose are interconvertible, all isomers of L glucose are also interconvertible amongst themselves, and all the isomers of D mannose are also interconvertible. So understand that when I say all the isomers of D glucose, I am deliberately excluding stereoisomers. I'm not saying that you can also take into account mannose as an isomer of glucose. They are isomers in terms of the molecular formula. Okay, but here we are talking about isomers that share the same DDLL configuration, or whatever the configuration is. For glucose in particular, it is DLDD. So each of these, all isomers, that is to say the alpha pyranose, the beta pyranose, the alpha furanose, the beta furanose, and the straight chain form. These 5 isomers are interconvertible with each other. And if I were to take any other sugar like say L-talose, then it would have 5 isomers which would in turn be interconvertible with each other. But we're not talking about conversions between the different major stereoisomers of aldohexose. Next, all these interconversions take place via the straight chain form. So you're not going to have any reaction wherein there's a direct conversion from say a pyranose to a furanose form. It's always going to take place via a straight chain intermediate, as I've illustrated over here. So here we have an alpha D glucopyranose sugar, and you can clearly see that it's alpha D glucopyranose, and the hemiacetalic linkage has been shown in a different color. This hemiacetalic linkage can be reversed in an aqueous environment into an aldehyde and an alcohol at these 2 ends. So this reversal is continuously taking place. Okay, as and when this reversal takes place back into the straight chain form, which itself had closed up and given us the cyclic alpha D glucopyranose form in the first place, another property is restored. That is the reduction property. You can clearly see over here that there is a carbon with a double bond O, the aldehyde group, which is being how do I put it, re-released. It was consumed in the formation of the hemiacetal. It is again being released, or it is again being developed when we open up the chain. And as a result of this, because this form is reducing, any of these forms which are interconvertible to this form will also be reducing. But if somehow I can block the opening of this ring and prevent its reconversion to the straight chain form, then what I'm going to do is I'm going to block this ability for it to reduce. Okay? So if I can block this, then I can block this as well, so to speak. But returning to the question of when this is actually happening, when you have this reversal taking place, there is another property that comes along with it. This interconverts to the straight chain form. The straight chain form then converts into the beta form or into one of the Furanose forms. Say, as I said, all interconversions take place via a straight chain intermediate, and all isomers can undergo interconversion. So this alpha form can convert into a beta form. Sorry. And in that case, the value of the specific rotation of this alpha compound, which is 112 degrees, will have converted into another value, which is 19 degrees. Okay. So the question we've got to ask ourselves is, if I have crystals of alpha D glucopyranose and I put it in water, how much of it will change into beta D glucopyranose with a specific rotation of 19 degrees, and how much of it will remain in the form of alpha D glucopyranose, which has a specific rotation of 112 degrees. Recall the basics of how we do these calculations. I am giving you another data point, that is that the mixture of these two sugars has a specific rotation of 52.7 degrees. The mixture, when both are in equilibrium, has a specific rotation of 52.7 degrees. Calculate the percentage of alpha D glucopyranose. So the question given was to find the percentage of alpha D glucopyranose at equilibrium values, right? And you are given here this data, the specific rotation and the corresponding form of the monosaccharide, of the glucose. 112 degrees is the specific rotation of the alpha D pyranose, 19 degrees is the specific rotation of the beta D pyranose, and 52.7 degrees is the specific rotation of the equilibrium mixture. Now, you're given these four options to choose from: 50%, 100%, 36.23%, and 63.77%. Okay, so let's see how you solve a question like this. Right, so you have, let's assume that the percentage of this guy, of the alpha D form, is X. So 112 into X plus 19 into 100 minus X is equal to 52.7 into 100. Opening the brackets over here, we get 1900X plus 93X is equal to 5270. That's just the equation you have to solve. So you get 93x is equal to 5270 minus 1900. That's 3370, and that implies that x is equal to 36.23% if you get it out. So option C is the correct answer. That tells us that when we look at alpha and beta D glucose, they exist in a particular equilibrium. They exist in an equilibrium where the alpha form is only 36% and the beta form, which is the most stable form, is 64%. Okay. Now that we understand the different forms that glucose can take, we can revisit those outlying reactions that we talked about at the beginning, which were the motivation for us to discover what the other structures of glucose could be. And we can now explain those reactions in several cases. The first one, if you remember, was methylation. We had spoken about how there are methyl glucosides that form when you reacted with MeOH plus HCl, and that these always form in two different forms. Now by now you might have guessed, since alpha and beta D Glucopyranose are the main forms in solution of D glucose, we should be seeing an alpha and a beta D glucopyranoside. Okay, so what is a glucopyranoside, or in general a glucoside, right? So you guys are familiar probably with the formation of acetals, and a glucoside or a mannose or a talloside, basically the name of the sugar plus ide refers to an acetal formed with that sugar. So first, the hemiacetalization process has taken place over here. You can clearly see we have an alpha D glucopyranose over here. Now we're reacting this with HCl. This HCl is a proton donor, and this is dry HCl. It's not done in the presence of water. So it's a proton donor to this sugar directly, and it comes and it protonates this alcohol, this alcoholic group over here. It makes it a leaving group, forms H2O and leaves. Okay, this will make this area a carbocation. This particular carbon will become a carbocation. Why is this carbocation going to form as opposed to the carbocations by the removal of any of the other alcoholic groups over here? Because this carbocation is resonance stabilized. Since there is a lone pair present since there are actually two lone pairs present, one will be in the plane of the ring. There is a lone pair which can resonate, which is present on the hemiacetalic oxygen. This will stabilize this carbocation. Then it will further react with MEOH, which is the reagent we're bringing in here. MEOH with HCl as the condition. MEOH will react over here, and this MEO part will function as a negative ion. It will come and it will get stuck on here, and you can see I've used a squiggle bond to donate this because and you will remember from our structure of ATP at the beginning of the chapter that a squiggle bond, or a bond denoted with a squiggly line, is basically a very easily hydrolyzable bond that is often done to release a certain amount of energy. So this is a very easily hydrolyzable bond, and because this had formed a carbocation, it was planar. When we added this back on, the OMe can go to the top or to the bottom. So we'll have an alpha form and a beta form, and this explains very easily why there are two different structures of methyl glucosides. Okay, this alpha and the beta form. Also note that this is only going to be degraded in the acid, an acidic medium. It is not base susceptible. This is only acid susceptible. But this will be it will dissociate in a very dilute acid. It does not require concentrated acid, but it will not dissociate in bases. So if by any chance I am performing my oxidative tests, recall that the Benedict's test, Fehling's test and Tollen's test all utilize basic media. Recall also that this was an important factor because that is what allowed fructose to undergo keto-enol tautomerization and thereby react with these tests, though fructose is actually a 2-ketohexose and not an aldohexose at all. Similarly, because this is a basic medium, it's not going to cause this bond to trigger, to dissociate. It will not trigger the bond to dissociate. As a result, none of the oxidative tests will be able to convert this back into the straight chain aldehydic form, and therefore this methyl glycoside, or rather these methyl glycosides, both the alpha form and the beta form, will be inert towards the oxidative test. These are non-reducing sugars. So I can also write that they are non-reducing. Once I put a strong basic medium in there, it's also going to cease its mutarotation. But in water or in dilute acidic conditions, the mutarotation will still go on. Remember that mutarotation and reduction are always associated phenomena. The instant I make it a basic medium, this bond can't be cleaved, so it can't release an aldehyde and become reducing. So therefore, it can't respond to an oxidative test, and it also cannot release the bond and turn back into the straight chain and then convert into the beta form. So the mutarotation is also lost in a strongly basic medium. There is a second way of methylating this thing. That is the reaction with Me2SO4 and NaOH. Okay. Now let's see what NaOH will do to a structure like this, to this alcoholic structure. You might already be able to see that all of these alcoholic hydrogens, because they are alcoholic hydrogens, are acidic. They are labile hydrogens. They will be removed by any base. And here we are adding a base. More than that, there is so much negative I, there's so much minus I effect throughout the entire chain because of the withdrawing effect of all the other O's, all the oxygens in the cycle, in the cycle as well as in the alcoholic groups. So this electron withdrawal will cause these hydrogens to be released as H+. They will be taken up by NaOH, water will be formed over here, and all of these will become O- ions. So the configuration here has been retained. Unlike here, the configuration will not be lost. The specific stereo configuration of each and every carbon will be retained, and then we will have this addition, and then they will all act as nucleophilic agents on Me2SO4. Each of these alcoholic groups will go and rob an Me plus from the Me2SO4 compound, okay, and they will form a whole bunch of OMEs over here. I have not bothered drawing out the Haworth projection. Just remember that whatever the initial stereo configuration is, the same stereo configuration is maintained here. Just every OH is replaced with an OME. Note another thing very carefully though. This particular one, because of the presence of this immediate neighbor oxygen, is much more susceptible to hydrolysis. None of these bonds are susceptible to hydrolysis. When you substitute this bond, when you dissociate this bond, it will form a stabilized ion, as we discussed, due to the presence of the lone pair of electrons over here. None of these bonds will be hydrolyzed easily. So this will hydrolyze in dilute acid, whereas these will all require the action of a concentrated acid. So keep in mind this fundamental difference between this OME and all the rest of these OMEs. If you perform this method and then you put it in a dilute acidic medium, this will hydrolyze very easily. Once it has hydrolyzed, so in a dilute acidic medium, this is a reducing sugar because this is hydrolyzable. It is also going to undergo mutarotation. But all of these are all fixed and these are not susceptible to hydrolysis. The second reaction that we have to consider, that was an outlying reaction in our original set of 3, is the reaction with acetic anhydride, and we employ NaOAC as another additional reagent or catalyst in this particular reaction. So what we do over here is when we react it with this is very common, right? You've seen before that when you have an alcohol and you react with an anhydride, it will form this kind of thing, this ester kind of thing. Actually, they are esters. And this is often used as protecting groups, which we've seen in a lot of reactions in other cases in organic. So once this is done, you have this particular bond, which is the acetylic linkage over here. That bond is acid hydrolyzed. So you can see I've used a squiggle over here again. It's acid hydrolyzed and it is not susceptible to bases. So again, any reaction taking place in a basic medium will not affect this particular compound. As in any reaction that requires glucose's aldehyde group to be free will not work if this compound is in a basic medium. It will only work for the acidic medium. So if you're trying to do your oxidation, etc., it's not going to work because most of your oxidative reactions take place in a basic medium. And so it's non-reducing. It does not mutarotate in basic medium. We're being very specific here. If you supply enough acid to hydrolyze this, then both of these statements will no longer be true. So the question that we were asked was to figure out amongst these 4 options, which of them will turn red in the presence of Fehling's solution. Okay. So beta D glucopyranose is basically just glucose sugar. It is a pyranose sugar, so it has formed a hemiacetalic linkage, but not an acetalic linkage. Okay, so it is clearly going to be hydrolyzed by Fehling's reagent, which is in basic medium, and so yes, beta D glucopyranose will turn Fehling's solution red because it will reduce the Cu2 plus to Cu plus, and Cu plus has a reddish color. Alpha D glucofuranose. Now this might put a spin on things because glucofuranose is less common. It occurs in minor proportion. You may not be familiar with its properties, but as you know, ultimately all different forms of glucose are interconvertible. This will also convert into the straight chain form in the presence of basic medium or acidic medium, or for that matter any kind of medium, except one that is so strong that it degrades it. So it will convert into the straight chain form. There will be an aldehyde present over there that will get oxidized to gluconic acid, and Cu2 plus will be reduced to Cu plus. So this also turns the Fehling solution red. Then we have methyl alpha D glucopyranoside. Recall that a methyl glucoside is only susceptible to acidic medium. Since Freling's test is an oxidative test that requires a basic medium, this will not be hydrolyzed. The aldehyde group will not be free. That will not be oxidized to gluconic acid, and consequently there will not be any reduction of Cu2 plus. So this will not turn it red. Finally, we have alpha L-glucose pentaacetate. Okay, so there is nothing to worry about the fact that the stereochemistry of this has been switched. This is just the enantiomer of alpha D glucose. Pentacetate means that there is going to be an acetyl group attached on every single one of the carbons present in the chain. Each and every one of these carbons will have, except C5 obviously, because that doesn't have a free valency for attachment, doesn't have any OH group. So all of these will be acetylated, none of them will be free to react. This will also not turn it red. So the correct answers are A and B. You've just been asked a subjective question. I hope you've taken the time to think about the subjective question that you've just been asked, which is, why is it that these two reactions do not give us products with glucose when other reactions like Benedict's test and other tests for aldehydes do give us products with glucose? What is it about these reactions that is different from a simple chemical perspective? And you were told to use the hint of the fact that it has to do something with equilibrium. So NaHSO3 is notorious for being a highly reversible, reaction. Okay, the same is true to a lesser degree of 2,4-DNP also. So let's see why that makes a difference. That makes a difference because when I have the aldehyde and the product with a low value of an equilibrium constant, then what's going to happen is some of this aldehyde will shift into the product, and that's enough. Okay, it's going to be a very small amount of aldehyde that will shift into the product. Okay, this is the case for 2,4-DNP. It is also the case for NaHSO3. However, when I have an aldehyde going to a carboxylic acid, and this is taking place via some oxidative pathway, obviously, then what's going to happen is that since this is more or less a unidirectional reaction, the equilibrium between the aldehyde and the cyclic sugar is going to be driven in one direction. The aldehyde will be steadily consumed as a carboxylic acid. Remember that the aldehyde is basically the open chain form. Since the aldehyde is the open chain form and it is being steadily consumed as a carboxylic acid, this cyclic form will be steadily converted into an aldehyde just to maintain this K value. Let's call that K dash. Okay, so if this is K for this carboxylic acid, excuse me, it's come out to be a little bit slanted, and this value of K is high for this reaction, unlike the K value for this reaction, which was for 2,4-DNP or NaHSO3. So what's going to happen here is that in the case of these oxidative reactions, your cyclic form of the carbon, of the monosaccharide, is going to be continuously converted into an aldehyde just to fulfill, because this equilibrium is being driven by the fact that this is a unidirectional reaction. Here, there's no such unidirectionality. These will attain a comfortable equilibrium with a very low value of product, and most of it being the aldehyde, and the aldehyde in turn will maintain its own equilibrium with the cyclic chain form. The cyclic chain form will not be continuously forced into the aldehyde form and thereby into the product form. And because of this, since these reactions are seen via precipitates, a yellow precipitate and a white precipitate respectively, there will not be enough product to precipitate, and we say that we can't see any reaction happening at all. But that's sort of a myth. Right, so now we're going to start a new topic, which is the conformational analysis of glucose, that is glucopyranose. We know that glucopyranose exists in two different forms, alpha and beta. We also know that any molecule that comprises carbon-carbon single bonds is free to rotate about those bonds, assuming various values of parameters known as dihedral angles, right? Which has to do with how these are organized. In the case of six-membered rings like this, we can take inspiration from the cyclohexane compound, whose conformations we have studied in some detail when we were doing the basics, fundamentals of organic chemistry. So from that we can see, what we remember from there is that the chair shape, the chair conformation has the minimum potential energy, that is the stablest conformation. So we've got to look at the two different chair conformations of alpha and the two different chair conformations of beta. Why are there two different chair conformations? Because obviously when you flip this chair conformation, it will change whether C1 is at the bottom or at the top. Okay, and in the case of cyclohexane, this didn't matter. Why didn't it matter? Because all of them had H's, hydrogens, both above and below. So you couldn't quite distinguish above and below. This side is pointing down, which means it's pointing towards an H. This side is pointing up, also pointing towards an H. Here on the other hand, when this side is pointing down, it is pointing along an H. When this side is pointing up, it is pointing along an OH. So the whole thing changes when it gets flipped. Whether it's up or down actually determines which of the substituents the plane of that portion of the ring tends to align with. And therefore these are distinct conformations. Now we need to select the stablest of these two conformations between alpha, because the majority of the alpha will be in the stabler conformation. Again, we need to select the majority of the stablest conformation in beta, and then we need to compare the stablest conformation of alpha with the stablest conformation of beta, and from there we should be able to deduce that beta is more stable, and that will explain why 64% of glucose exists in the beta D glucopyranose form in solution. Recall that in order to ascertain which one is more stable, we need to look at the fact that these bonds are not actually as long as you've drawn them. These are not to scale. Actually, this bond is just twice the covalent radius of these carbon atoms with the polarities that they have in this particular molecule. So you can think of this as being, roughly speaking, the diameter of an atom. Since this is the covalent radius, this is one more covalent radius. This entire bond length is roughly the diameter of one carbon atom. So obviously that distance means that this H and this OH, these two groups, will be in physical contact with each other. Basically, the fewer the axial substituents, the more of the axial groups are hydrogen, the more stable they'll be because they won't touch. The more bulkier groups are present on the axial position, the more steric hindrance they're going to be, and the quicker the dihedral angles will change to adopt a new conformation. So let's perform a very simple analysis over here. This is the bottommost point in the entire ring. So whichever substituent is at the bottom in the alpha isomer at C1 is going to be axial, and that is OH in this case. Remember that in the alpha, OH is at the bottom, and in beta, OH is at the top. So this OH is at the bottom. Over here, H was at the top. Since this carbon is locally at an upper point, the group on the top ends up becoming axial. This carbon is locally at a bottom point, the group at the bottom becomes axial. This one at the top, so the group on top is axial. This one locally at a bottom point, so the group on the bottom is axial. So this way we identified what the axial groups are. There's one OH and there are 1, 2, 3, 4 H's. The remaining bulky groups, this is the OH here, the OH here, the OH here, and the methyl, the MEOH here, CH2OH. These are all equatorial, and so they don't cause any kind of steric hindrance. When we flip the chair, on the other hand, all of these that were axial end up becoming equatorial and vice versa. So while this OH has become equatorial now, all the other OHs like this one and this one and this one have all become axial, and worst of all, this MEOH has become axial. So clearly the former is the more stable out of the two isomers. Now when I look at the beta compound, in the beta compound, the beta isomer, what's going to happen is that this is going to be switched down, the OH and the H over here, because that's the definition of beta. It's a C1 epimer. That's what an anomer is, right? When two sugars are anomers of each other, they're basically C1 epimers. So the beta anomer is going to have this thing switched around, but the rest of them will all be the same. Again, for the flip chair, the rest will all be the same. So in this particular case as well, this one is the most stable in beta, this one is the most stable in alpha. So we know that we can ignore these two. These two are the less stable ones. Comparing the stablest ones, what we can see is that this guy has one equatorial OH, but this guy does not have a single equatorial OH. Therefore, the beta anomer possesses the stablest conformation we have. And this is one of the reasons why glucose is such an ubiquitous sugar, right? You may have heard of galactose and mannose and the rest of them before, but I bet you that from 6th grade, 7th grade, you've been hearing about glucose and more glucose and all its varied uses in the biological world. It forms this extraordinarily stable structure with absolutely no axial OHs in its major form, and therefore it is one of the most stable monosaccharides we have. There are two other reasons why glucose is favored in the biological world, which we'll come to in our section on polymers of these. I'd like to leave you with a question. You can pause the video and attempt it. It's a slightly harder question. Essentially, take the molecule fructopyranose. Take the molecule fructopyranose. That basically means that if this is C double bond O, COH, sorry, OH is on this side, CH, COH, H, COH, H, and this carbon over here is a CH2OH. Then this is where the hemiacetal link will form, and this whole thing is going to form a pyranose ring, not a fructofuranose ring. Once you've got the fructopyranose ring, I want you to try and reduplicate this exercise with alpha and with beta. There will be a slight difference over there, you'll have to think a bit, because unlike here, the alpha and beta won't both have the same most stable conformation. One of these will be more stable for alpha, one of these will be more stable for beta. Okay? Take the most stable one for each of them, then do your comparison and check which one is most stable. So all you really need to know from this section, because it was really complicated and some of the problems are quite intractable, is that for glucose, beta is greater than alpha in stability, and for fructose, alpha is greater than beta in stability. And this is all you need to know for all your questions. Question that you've been asked is to find the which of these will react with pH, NH, NH2, phenylhydrazine, to give osazone. So it's very specific. You need to have 3 moles of reactant, right? So it will give osazone, not just a phenylhydrazone. So the first is D Glucopyranose. Now we know that D Glucopyranose will undergo interconversion to the straight chain form. In the straight chain form, there will be an aldehyde, and right next to that, there will be a hydroxy group. The first two groups are one aldehyde and one alcohol group. So they will react and they will form an osazone. So yes. The second is D-fructofuranose. So again, I've got a fructofuranose that will also undergo interconversion to the straight chain. In the straight chain, it has a 2 keto group, and the first group is an alcohol. So again, it will form an osazone with those two. We know that in fact glucose and fructose form the same osazone because the remaining steel centers have identical configuration. Then we have 3-deoxy-D-glucose. Now this is a trick question. If you had 2-deoxy-2-glucose, right, then the second carbon would be missing an OH and you won't have an osazone forming. But here the third carbon is missing an OH. That doesn't do anything at all. Osazone will still form with the first and second carbon, the aldehyde and with the OH. So this will also show us an osazone. The final is the pentacetate of D-glucose. So this boils down to a very simple question. Pentacetate has that squiggly bond which is easily hydrolyzable. Will it hydrolyze and give us the rearrangement, or will it not hydrolyze? So if you have pH, NH, NH2, what medium will this compound be stable in? This compound itself is basic. If you put it in an acidic medium, it will react, it will not be stable. In a neutral medium also there is a slight amount of acidity, right? Water always has, because of that pKw, this 10 to the power minus 7 H plus is there. So it is properly stable in a basic medium. If you are doing this in a basic medium and this compound also is basic, there is no way that this is going to react, because the dissociation of this squiggly line bond is triggered by an acidic medium for both the pentacetate and the methyl glycoside. So this will not break down. Since it will not break down, It cannot undergo the interconversion. So there is going to be no interconversion to straight chain. Since there will be no such interconversion, the aldehyde group will never be freed, and so there is not going to be any position formation. So the answers are A, B and C.